So today we're going to start with section 1.1, which is about problem solving. We will see just a couple of things at the beginning here, and then we'll finish it up next class period. To start with, this is one of those places where I'm like, there's a lot of writing. I don't want you to have to write all these down. Aren't you so glad you're looking at my notes, right? Oh, yeah. So there are a lot of problem-solving strategies, a lot of structures, and this is one of them. This is the one that your book does. So this is a 4-step problem-solving process. So the first step is to understand the problem. So these are some of the kinds of questions you ask yourself, making sure you understand the problem. Can the problem be stated differently? What do I need to find, or what is needed? What are things that I don't know? What information am I given? And what information maybe is missing or is not actually needed even though I have it? Because that's real life stuff where you have like all sorts of information you have to sift through. What do I really need to know? So once you kind of have a good grip of what you're being asked to find, you need to figure out how you're going to find that. So it's devising a plan. So there's a list here of, it says non-exhaustive. That means this isn't the only possible problem-solving strategies, but these are some that are common. And I'll show you, some examples of some of these starting today and finishing next class period. Looking for patterns is one. Examining related problems. That's what you do all the time in math. You go back and you look for something in the notes that the teacher did that looks like the problem you're working on, right? Yeah. Examining a simpler or special case. Sometimes if you make something a lot smaller, it becomes a lot easier to work with, and then you can figure out how to make it bigger and use the same idea. Or making a table or a list. Do you have anybody who's list makers in here? Does anybody write things down on the list just to cross it off later? Okay, cool. I'm in good company. Me too. Identifying a sub-goal. Sometimes it's easier to think, okay, if I could just get to this point, I think I could finish it from here. And so I just have to work on the first part of the problem, so to speak. Making a diagram. Even if you're not a good artist, which I'm a terrible artist, sometimes a diagram can be very helpful, especially if it is an imagery kind of problem. And we've got an example of that that we will see as well. Believe it or not, guess and check is a valid strategy. I know, somebody's probably told you along the way this is not good. Randomly guessing and checking is not the best idea. But if you're thinking about it in an organized, structured way, it can be very useful. Working backward, I know you guys have done this before. This is what happens when you look at the back of the book and you say, they got the answer 52. How did they get that? Right? Yeah. So we're going to see some working backward type questions. And then the last one is actually to write an equation. We're going to steer clear of the equations for the most part, not because you can't use them. It's perfectly fine if you can and want to use them. But most of the things that we work with in this class should be accessible to children in early grades. And equations are not as accessible in their early grades as they are later on. And so we're going to stick with some of the more basic kind of problem-solving strategies because I want you to realize that equations aren't absolutely necessary to solve everything. Unlike you kind of were told maybe in algebra or algebra 2 in high school, right? Got to get an equation, got to get an equation. It's not always needed. So we're going to take a look at some other possibilities. Once you decide on what you're going to do, you can do it. All right, you're going to carry out the plan. So implement a strategy, perform any needed calculations or processes. Be careful to attend to precision in language and mathematics. So be careful, right? If it says 5 times 4, make sure you really did 5 times 4, not 7 times 4, whatever. Those kinds of small things. To check the steps along the way, either formally, that means like making sure that the mathematics is absolutely correct, like I really did 5 times 4. But also intuitively, like, does that make sense? All of a sudden, I got a decimal number of babies being born. Something's wrong, right? That kind of stuff, right? Does what I'm doing make sense? And then keep an accurate record of your work. So one of the things that drives me crazy with my 5th graders right now is that there's no place to do the work where they are, so they're scattered in their work everywhere, and then we can't go back and fix something. They just have to start from scratch on a problem. Don't create more work for yourself. Keep things organized enough that if there's a problem, you can go back and find it and fix it to save yourself time. And then checking your work. And then there's 2 things to checking your work that I kind of already mentioned as you're going along the way with carrying out the plan. Deciding if the answer is reasonable, decimals and negatives and things like that. Did it make sense in the problem? but then also checking the accuracy of your result. Okay? Is the mathematics actually correct? All right, so we're going to do some examples. That's what we're going to do. We're going to attempt to do 2 problems today. The first one is a gentleman by the name of Gauss. So Gauss is a famous mathematician. It is Gauss. When he was in early grade school, like first grade, his teacher actually gave him in the class an assignment intending to take them a good deal of time. I'm sure you would never do this to your classrooms. Just give them busy work. That's not what you would do. No. She asked them to find the sum of the numbers from 1 to 100. So she anticipated they would do 1 plus 2, they'd get that answer, and then they'd do plus 3, and they'd get that answer, and they'd do plus 4, right? Got the idea? And that would take a fair bit of time, right? Sure would. Unfortunately, that didn't work out for Gauss. Gauss gave her an answer very, very quickly. And what I'd like to show you is the method that he used to do so, because it's a very useful method. And he did it by looking at patterns. So the first thing I'd like for you to do is to write down S. S is just standing for the word sum. It's a sum. And write down the first 3 numbers from 1 to 100, so 1, 2, 3. And then you can put a dot, dot, dot. And then the last 3 numbers in that list, so 98, 99, and 100. This is what the teacher wanted them to do. Maybe not in this like visual, but this is what she wanted, right? Yeah. So here's what Gauss did. He took the numbers and he said, well, let's just reverse the order and see what happens. Okay, so I'm going to write the same statement down underneath this one, but in reverse order. So it's still S. It's just that I'm starting out with 100, and then 99, and then 98. And eventually when I do my dot, 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 I have 3, 2, and 1. So here's what I want you to notice. Let's think vertically, like adding vertically. What's 1 plus 100? 101. What's 2 plus 99? 101. What's 3 plus 98? 101. And it always works out to being 101. It's a whole bunch of 101s, right? Yeah, it is. And so what we end up happening, what happens is we get a bunch of 101s. Wow, so when you add the same number together a whole bunch of times, there's a shorter way to doing that. What is it? Multiplication. And you might pause here and think like, now wait a minute, he's in first grade. Did you know that it's not always been the case that addition was taught before multiplication? When my grandmother was first learning mathematics, she's told me this before, before she passed away, is that they learned multiplication first. Isn't that interesting? So we have a whole bunch of 101s, and it's a lot easier to do 101 added together against itself a whole bunch of times if we use multiplication. But what we need to know how many 101s we have. Any ideas? How many of them are there? There's 100. How do you know? Because the numbers went from 1 to 100, right? There's 100 numbers there. Absolutely. Now, if it didn't start at 1 and didn't end at 100, which we'll have happen in a minute, we have to be a little bit more careful, but there's 100. I'll say of these. There's 100. So, I really have, by the way, I don't think I wrote that. Please fix this because I have an error on my screen. This should say 2S. Why should it say 2S? Because I added S and S, right? I've got double the amount. Okay, so I realize I'm writing that in sort of an algebraic way, and I'm sure that's probably not quite what Gauss did, but he said something like I doubled the numbers or something. Okay, so but for what we're doing, we're going to write 2S. And this is 101 100 times, so it's 101 times 100. What is 101 times 100? Not a trick question. It's 101, and then what? 2 zeros in the end, right? Just multiplying by 100. Oops. And then what would I do? Because I don't really want to know what 2s is. I want to know what s is, what the sum was. Yeah, we would divide by 2. Okay, so what's 10,100 divided by 2? Don't overthink this. You guys can do this. Bunches of ones and zeros. About, yeah, 50-50, 5,050. 5,050. So this is basically what Gauss did. Did he write it quite like this? Well, no, not necessarily. Another way that I've seen it written, instead of writing it the way that I did where I added it vertically, which I think is very handy and very friendly, is I've seen it drawn like this before, and I kind of like this one too. Whoops, I changed that. Is that they've drawn the pairs together like this. You know, where they sort of just paired things up in sort of these arches. We're still doubling it when we do that. We're still getting the same number every time. Okay, so let's try a similar example. This is an examining a related problem. So we're going to use this idea of what Gauss did with patterns, and we're going to do it again, but now notice the numbers are not 1 to 100. They're 36 to 147. Okay, but we can do the same process. So if you want to do it the way that we did it before, you can rewrite it. If you want to draw the arrows and pair things up, that's fine too. It doesn't matter to me. But you know what? I think I'll do it like this since I've already got it written here in the middle of the page. S equals. And then we're going to do the same thing again backwards. So I've got 147, 146, 145. And yes, I realize that I'm not writing all of them out, and it doesn't really matter. They're going to all pair up, so I'm just going to put the last two here, so 37 and 36. So I've doubled my values because I'm adding the values twice, right, to themselves. So what does each of those vertical sums or arching pairs that you've done, what do they add to? Right, so what's, whoops, that's not what I meant to do. Wow, that's not either. There. It's 36 and 147. What is it? 183 is right. And are they all 183? Yep, they are. They're all 183. So I have a bunch of 183s. And the question is, how many 183s do I have? So this is a little trickier than the last one, because the last one started at 1 and it went to 100. I had 100 numbers. But here I'm starting at 36 and I'm going to 147. How do I figure out how many numbers I have? What do you think? You are super close. So here's what I've got. So Brooklyn suggested I take 147 minus 36. And that's really, really close. It's actually 35. Do you know why, Elizabeth, or can you explain why? Not sure? Okay. It is 35. There's several ways you could explain it. The one that I like is the fact that let's pretend for a moment that it started at 1 and went to 147. Okay? If it went from 1 to 147, how many numbers would we have? 147, right? But the first 35 that I just sort of imagined aren't really there, are they? So those 35 that I sort of included in my argument just a minute ago to go from 1 to 147 need to be removed from the 147 that I have. In terms of thinking about it for future problems, what I suggest doing is remembering that you subtract the number that's in front of the number that you actually have. It's the one that comes before it. You have to be a little bit careful, though, because sometimes there's a pattern to the numbers that doesn't increase by 1, right? Like all these numbers are nice in the sense that 36, 37, 38, 39, they're all there, right? But what if it were skip counting? What if it went, 3, 5, 7, 9, 11? What if it were all odd numbers or multiples of 5? What would I do then? Well, I need the number that comes before it in the pattern. Whatever the pattern is, that's the number I'd be subtracting. Does that make sense? Okay. The other thing, so when I subtract these, I will have the right number. So what do we have, 112? I have 112. The other thing to notice is that it's 112 because I have all the numbers. So let's say again that it were skip counting. Let's say it were every other number. Well, let's do an easy one. Let's say we did the numbers from 1 to 100, but we only did the evens. How many even numbers are there between 1 and 100? 50. It's half, right? Well, why? Because it's every other, right? I mean, I'm getting half the numbers. So if it were skip counting by 5s, multiples of 5, I'd divide by 5 because I have every fifth number. If it were skip counting by 3s, right, if it's counting every third number, I'd divide by 3. So we have to remember that step of it too in case we've got some skip counting going on. Neither of these skip counted, but you have some in your homework or group work that will. So just be aware of that. So I have 112 of these. So I'm going to call them terms. There's 112 terms. So what I really have is I have this 2s, and it's 183 times 112. So somebody's going to have a calculator, right? Who has a calculator with them today? Do you have one? Okay. If you'll multiply for us, what is 183 times 112? This one we don't do in our head. At least I don't. $496? Okay. 20,496. Am I done? Almost. What's the last step? Yeah, divide by 2. I'm removing the double counts. That's why I'm dividing by 2. So what is my sum when I divide by 2? 10,248. Any questions on that one? Cool. All right, and that's where we're planning to stop today. So I'll be posting this out online. You don't need to do any homework. Just come back and see me again next time, and we'll continue.